What are we mainly discussing today? Students, we will mainly discuss how to reduce the scope of EIGRP queries. So why do we need to reduce the scope of our EIGRP queries? It's simple. For a large network, if we deploy a network using EIGRP, the network might be quite large, right? There are especially many routers. Perhaps the number of routers is considered many, or say switches, right? We might all be running protocols, right? For instance, running EIGRP. Students, for instance, if we run EIGRP, then we need to consider an issue. Regarding EIGRP, if in a network environment running EIGRP, we lose a certain successor route, the transmission of this successor route entry, this root entry, for example, for the devices below, such as this is an access layer device, above it is the aggregation, or what we call our core. For our access layer switches, then do we access more external route entries, or do we announce more root entries into our network? Is it more route entries given to us from above, or do we give more route entries upwards? Is it not that we receive more from above? Then we just announce our access network's route entries to our aggregation layer routing switch neighbors, or say to our devices above. Above then transmits the route entries to other neighbors, spreading everywhere. So in fact, our access layer devices learn many route entries. The route entries sent out are relatively few. But students, suppose due to these devices above, we lose a certain route entry, and it just happens to be a good successor route, and it is also one they themselves announced. For example, the router above I announced a 1.1, 1.0/24 route. So it is I who announced it. Then I tell this route entry to our switch, then I learn the 1.1, 1.0/24 route entry. Right. I move upward. Then I learn another route entry, 1.1, 1.0/24 route entry. I move upward, and then we learn the route entry from them. I know the 1.1, 1.0/24 route, go this way, go left. Then we learn below the 1.1, 1.0/24 route moving upward, 1.1, 1.0/24 moving upward. So if a network environment is especially large, and at this time within the network, if we lose any route entry, for example, if I lose the 1.1, 1.0/24 route I announced, or say when we are announcing entries, I have filtered it. I won't announce this route entry to you. That's possible, right? Maybe I filtered out a route entry, or I directly delete a certain route entry. So what situation will there be at this time? We talk about the query mechanism, right? So we lost such a successor route. We lost a successor route. What to do? Send queries to all neighbors, right, students? So once we lose a certain route entry, I will send queries to all neighbors. I send a query message. Where did this route entry go? Is there any other path available? But actually, this route entry is reported from above. You're out of route entries, and you're still querying me here. I still have to look everywhere. I still have to ask everyone. So if the network environment is particularly large, then these query messages will spread throughout the entire network. For example, we have so many routers running the EIGRP dynamic routing protocol. You lose a route entry, everyone will send out this query message. Then suddenly a bunch of queries will appear. A bunch of ACKs, a bunch of reply messages. Right, students? So we should try as much as possible to say, in such a network, suddenly so many messages appear, so much traffic. Isn't it definitely going to consume resources, right? We need to figure out what to do. Perhaps the devices below, the receiving layer devices. Your hardware is not particularly good to begin with. Your hardware is definitely not as good as the core. And it's a bit cheaper, so suddenly you see so much traffic coming in, so many queries coming in. Our hardware might not be able to hold up. So what do we want to do? We want to reduce the scope of queries. Can we not query so much? Your query messages, can we not send them throughout the network? To every nook and cranny? Can't we quickly end the queries? Otherwise, your query messages are like broadcasting data packets flooding everywhere. How are we supposed to manage this? We can't keep doing this. We need to reduce its scope. Secondly, we can speed up its convergence. After reducing the EIGRP query scope, we can improve its convergence speed. Let's talk about a very obvious example. Suppose, just like our diagram just now, 3 routers, 4 routers, 5 routers, 6 routers, This is R1, then 1.1. 1.0/24 comma, we announce this route entry to our EIGRP neighbors, like this is R1. Behind it is R2, this is R3, this is R4, this is R5, this is R6. So suppose I'm R5, I learn your route, 1.1. 1.0/24 comma, do I go? You go. Who goes through R1? Then I pass the route to R3. R3 takes 1.1. 1.0/24 through R2. R4 takes 1.1. 1.0/24 through R3. R5 takes 1.1. 1.0/24 through R4. R6 takes 1.1. 1.0/24 through R5. Then the route entry is announced by R1. But students, what if R1 loses a route entry? Even though the route entry was announced by me, entered into my own database, I myself, as the originating router, announced it to our EIGRP neighbors. But since it was announced by me, there definitely won't be any feasible successor, right? What to do? Losing the successor route with no feasible successor route, I send query messages to my neighbors. Correct. This route entry was announced by me. But now I don't have it. I still have to send queries to ask others. Clearly, it was a route entry announced by me. Then R2 realizes who's next for me. After I respond with an ACK and realize the next one is you, my route entry came from you. You tell me you don't have the route anymore. I look further back. I check further back. Because you, as the originating router, lost it. It causes all other routers in our network to accompany you in completing a query and convergence cycle. This is also a problem. In this way, obviously, the message is that the route was announced by you. Yet you query and search extensively. Until we respond later, reply. After the reply, I will finally remove the route entry, remove the database entry from my database. Clearly, it's not necessary. Students, clearly the route entry was announced by me. Clearly, it's unnecessary to have such a broad query scope. Where are you looking? Wait for his reply. Then I'll delete the database entry. The query speed is too slow. So we will try by all means to, in our network, reduce the scope of our EIGRP queries. Reduce the query scope so as to make our queries quick, accurate, and effective. And also, it could reduce the resource usage of our devices. This is our ultimate goal. Students, to explain this concept, we break down this experiment. We can use just 3 routers for this experiment: R1, R2, and R3. These 3 routers are enough to complete the experiment. So we disconnect the link between R1 and R3, just unplug the cable. Physically disconnect it, then the 3 routers. Okay, no problem. How is there still a neighbor relationship? Clear IP EIGRP, no need to clear it. Okay, beyond the hello time, beyond hello, beyond the time, no more hello packets received. Then, the neighbor relationship between the 3 routers. Now, in this situation, let's explain how to reduce the EIGRP query scope. Suppose R1 announced 4 routes. We have the 100.1, 0.0/24 route entry, the 100.1, 1.0/24 route entry, the 100.1, 2.0/24 route entry, 3 routes already, 100.1, 3.0/24, 4 routes now. Suppose R1 announced these to the network, these 4 detailed routes, given to R2 and R3. Doing this on R1, as usual, we create loopback 100, IP address 100.1, 0.1/24, loopback 101 IP address 100.1, 1.1/24, loopback 102 IP address is 100.1.2.1/24, loopback 103 IP address 100.1, 3.1/24. Then we announce all of them into our EIGRP database, 100.1.0.1 precisely announced, 100.1.1.1, 100.1.2.1, 100.1.3.1. We precisely announce. So these 4 routes will be placed into our EIGRP database. This generates corresponding database entries. Then we inform our neighbors. So on R2's side, there will appear a show IP route. We will receive the database entries it provides, calculated as detailed routes committed to the routing table. Next is R1. Similarly, on R3's side as well, show IP route. Then we can learn these 4 route entries. Now, if for us at R1, if I lose such a route entry, I will send queries to all my neighbors. Everyone will send out queries. We capture a packet between R2 and R3, add a packet, we capture a data packet between R2 and R3. So now, if on R1's side, we disconnect a certain interface, a certain command interface, like interface loopback 100, we shut down loopback 100. Here we miss typing a 103. No problem, it doesn't matter. We disconnect loopback 100. After the interface is shut down, we will immediately lose the directly connected route. Students, after the interface is down, the directly connected route is gone. Then, stored in our EIGRP database, this directly connected route, the interface's directly connected route, stored into the EIGRP database. After the directly connected route is lost, of course, the database entry will also be lost. After it's lost, we lose that successor route. Then R1 will send out query messages. Your move, losing the directly connected route. You see R1 immediately sends out a query. Sending the query. Over here, students, because this route entry was the only successor in my database, losing the successor with no feasible successor, we just had to search. So in this way, you see, I announced the route entry to R2, R2 to R3. It's clear my route entry was lost. Yet I kept querying for a long time, waiting for R3's reply. R2 then sends us the reply. We only then remove the database entry from my database. It was really deleted. We go to show EIGRP topology, achieving rapid convergence. But in this way, it feels actually unnecessary, right, students? So we discuss the first method, limiting the EIGRP query range, the first solution. By summarizing to limit the EIGRP query range, how does summarization limit it? Students, let's look at EIGRP's query mechanism, the characteristic of its sent queries, the feature of EIGRP query mechanism. So, the queries I send, pay attention to what? The query messages, what I send, what I seek in the queried route entries. 100.1, 0.0/24 comma. It's the detailed information of this route entry I query for 100.1. 0.0/24 comma, what's the status of this route entry? Is it still reachable? Students, what you need to pay attention to is when I, R1, lose a route in my database. 100.1, 0.0/24 comma, the detailed route. After that, the query messages I send are also about this route, 100.1, 0.0/24 comma. What route I lost? I query about what route entry, ask about the detailed information of this route entry. So you need to be aware, EIGRP queries are strictly matched. What is strict matching? Whatever route I lost, I query about that route. I ask you, do you have a 100.1, 0.0/24 route entry? So the queried party, when they receive the query message, they check this route entry, which is 100.1, 0.0/24 comma. Then it must exactly match, or it's called precise matching, strict or precise matching. It must be. It must query the same prefix and mask of the route entry. It must be exactly the same. If it looks different, then it's as if it doesn't exist. What does this mean, students? When we, RA, lose a route entry, we query for 100.1.0.0. It's the -24 route entry. So suppose we, R2, don't have this route entry, or can't find this exact one, completely the same route entry. What to do then? We have the first situation. If we don't have the route entry, this route entry related information just replies. Reply what? Route entry unreachable. Then our query sender will remove the route entry from the database. So using this summarization scheme, we can very cleverly and quickly limit our EIGRP query range. through our querying mechanism, how to do it. For example, we do such an event, we do a summarization on R1. We've already talked about summarization, manual summarization method. So R1, we announce these 4 detailed routes to be sent out. We can summarize these 4 detailed routes into one summarized route, a single summary route of 100.1. 0.0/24 for the summary route, consolidating the detailed routes into a single -24 mask route entry. All 4 routes are summed up together, only announcing one summary route. After summarization, it's quite different, like the zero interface IP summary address, EIGRP 90, announcing our EIGRP 90 routed entries, these database entries. All of these matched by our summary, summing up the detailed routes. 100.1.0.0. We could add a question mark. Directly enter -22, that works too. Sorry, I wrote it wrong here. -22 mask route entry. Entering -22 also works, of course. Entering the correct subnet also works. 25.25.25. 2.0 comma. We summarize these 4 detailed routes into one, A100.1. 0.0/22 summary route. Then in R2's routing table, it will lose these 4 detailed routes and instead will have a 100.1. 0.0/22 summary route entry. Now we can significantly reduce our query scope. For example, let's do an experiment. Now on R2's side, we have only one route, the only one, a 100.1. 0.0/22 route entry. The next address is R1, so after R2 has no detailed routes, we naturally announce out, telling R3's route entry is also a 100.1. 0.0/22 route entry. R3 also will have no detailed routes, only one summary route. So let's say we also summarize R3 to one summary. If, at this moment, R1 loses another successor route, like loopback 101, our loopback 101 corresponding direct route, if we also lose it, I directly delete this interface. Then simply, R1, of course, sends a hot message, querying this lost route without a feasible successor route entry. Are there any other paths? We cut it off, so R1 immediately sends a query. You see, R1 sends the query message to my neighbor. Broadcast address sends. When the hot message is sent, the query is for 100. 1.0-24 comma this detailed route. Then R2 responds with an ACK after what's his answer. R2's answer is, this route entry. Sorry, I have no information about any route entry. Its delay is infinite. I simply can't reach this route entry, can't reach this network. Why? You're querying for 100.1.1.0. R1 lost the route for 100.1.1.0. He queries for it too, 100.1. 1.0/24 route entry. Students, what I lost is it. I query for it too. Then, when R2 receives the query message, he must match it exactly, completely and precisely. It must be the exact same route entry for me to be able to query it. And when I look in my routing table, there is simply no such route entry. In my database either, there is no such route entry, meaning I simply can't get there. Even though I can actually access this segment, I have a summary route, I can access it. But you're querying for this detailed route. If I don't have it, I just don't have it. If it looks different, then I'll quickly reply with a reply. I don't have this route entry. Can't reach it. It's just that simple and blunt. Think about it. Originally, R1 actively announced route entries. After loss, it might query R2. R2 discovers it's R1, then has to send a query to R3. Result: waiting for R3's reply, then R2 replies. This is our third query condition. But now, because we've summarized, we essentially need to query R3. This query message, once it reaches R2, it's immediately blocked by us. So R1 can immediately get the message that the route entry is unreachable. Quickly remove this entry from my database. We've greatly reduced our query range down to just R2, because we made a summary, reducing its query range. Of course, its querying is very strict. Even if the prefixes are the same, it won't work. For instance, let's do this experiment. Now, I'll restore our R1's loopback 100. Interface loopback 100, no shutdown, restoring our loopback 100 corresponding direct route. Then at R1, show IP EIGRP topology, the database now has 100.1.0.0, 24 detailed route. Doing this, if we say loopback 100 falls off, we lose this database entry of detailed route, 100.1.0.0. Send a query message. We will also query this 100.1.0.0, 24 detailed route. What will R2 reply be? The reply is, sorry, this entry I can't reach. Infinity, unreachable. It's infinite. Why? So the query you made, we lost 100.1.0.0. We query for it too, 100.1, 0.0-24, comma, this detailed route. We send a query message, querying for this detailed route. Do you have a 100.1.0.0, 24 route? Do you know how to get to this site? Do you have its route? Can you tell me the information about this route entry? For R2, the query message I receive, you're looking for 100.1, 0.0-24, comma. I don't have it. I only have 100.1, 0.0-22, comma. It looks different. Students, although I can access it, sorry. What you are looking for is not what I have. Anyway, you're mistaken. There's no such person. I don't have his information. Although I can access it. I don't have the exact same information. Sorry, then it's unreachable. I directly reply with a reply. R1 then very quickly completes an EIGRP query, quickly removing this entry from my database. I know it's unreachable. That's how we reduce our query range. That's our first method, by summarization. Both reduces our route entries. Look, so many detailed routes became one summarized route, and we can also, through this type of summarization, reduce our EIGRP query range, achieve the maximum extent of reducing our device's resource consumption and our querying processing time. So by using summarization, this is our first method. Of course, this method is a bit of a trick. We use its query matching mechanism to achieve the limit. That's how we do it.